Let's talk about vector functions. So these describe roughly curves in space. So previously we've used parametric equations to describe a curve in 2 dimensions. Well, we can do exactly the same thing in 3 dimensions. So we've done this already for the simplest graph, which is a straight line. So it's on the left side, you can see it's in 2 different notations. The bottom one is sort of the standard form that we like to use, where we see one given point, 3, 1, 3, and then a direction vector 1, 2, -4 times the parameter variable t, and then r equals that. So we can also put this all together as a single vector. So it looks more like a single function. So that's the first notation. R of t equals 3 plus t, comma 1 plus 2t, comma 3 minus 4t. And the graph, as we know, is going to look like a line, and that's depicted in the graph there. Okay, so now we are going to go to the more general case. So, for example, r of t equals sine of t, comma cosine of t, comma t. So let's take a look at the graph and then try to make some descriptions here. Okay. So on the right side, you can see the graph. Let's talk about that. So we can pretty directly connect the formula to the graph. So for example, if we just stopped after x and y, you'd have x equals sine t, y equals cos t. We're familiar with that. We know that that is the parametric equation for a circle, radius 1. However, now that we've added in the z-coordinate, what's happening? As t gets bigger, in other words, as theta is increasing as we're wrapping around the circle, the z-coordinate is increasing. Therefore, what you get as a result is a corkscrew. In math, this is called a helix. So now note, for example, if you look at the graph from above, you would just sort of be looking straight onto the xy plane, and you can imagine all you would see is a circle. Of course, this graph only shows a piece of the graph for certain t values. T could go from -infinity to infinity. You would have an infinite helix. Now, of course, for each of these x, y, and z coordinates, we've put some particular simple functions in here, but you could have any function. And so, in general, we would have to rely on software to plot the graph for these things, which are a vector function, also called a space curve. So let's look at a slightly funky one. Here we go. So here r equals 3 minus t, comma t squared, comma cos t. And that produces the graph on the right side. So what does this graph actually look like from different perspectives? Because it's really a 3-dimensional graph. So first we're actually going to do some solving. So from straight ahead, from the graph that we've drawn here, you would see it from the x, z perspective. So x on the horizontal axis and z on the vertical axis. And you would not be able to distinguish y values. So the graph, just looking at x, z coordinates, would be 3 minus t cos t. So if we solved it out, we would get that t equals 3 minus x. So since z equals cos t, then z is just cosine of 3 minus x. So it's a sort of cosine curve from that perspective. So what about from these other perspectives? What about the xy perspective? Well, written out as a formula, xy would equal 3 minus t, and t squared. So we can solve for that. First, you can solve for t, so t equals 3 minus x, and then from that we would have that y equals, just substituting, 3 minus x squared. So you know that this is basically a certain parabola. Now what about from the yz perspective? Well, written as a formula, we would have yz equals t squared cos t. So what can we do with that? Well, neither of these is particularly nice to solve for t. We're going to pick the first one, it's a little better. So using the first equation, you'd get t equals the square root of y. And then from that, you could say that z equals cosine of rad y. It would kind of be a cosine curve, but it'd be a pretty funky one. So I happen to have this graph plotted in some software, and this software is going to actually let me drag the image around to look at it from different perspectives. So suppose we just want to look at it from the xz perspective. We drag it around, and it's looking something like that. So what you can see is that more or less this looks like a cosine curve, just as we calculated. So now let's look at it from a different perspective. What about from the YZ perspective? So notice that we've got Y over here on the vertical axis, and let's see, X is here on the horizontal axis. Well, you can see more or less what we've got is a parabola. And that was, just as a reminder, xy, that is what we had calculated. Now, let's take one more look. What about swinging around here? Now, what about from the YZ perspective? So it's going to be a little weird because it's three-dimensional, but let's take a look. There we go. Okay. So in this case, from the YZ perspective, make that line up. It's a little hard to get the perspective right, but there you go. From the YZ perspective, what we see is this thing kind of swooping down. But if this graph were to go on forever, it would actually go up, down, up, down, up, down. To the right. To the left, you'll notice that it stops. And that, if you recall, matches exactly with what we were saying. Z is the cosine of rad y, so it's a cosine curve, but notice that rad y will always be a positive number, so we've always got positive impulse. So anyway, if you have this fancy software, you can actually take a look at these different graphs. So that's a quick introduction, or really an extension, on what we've seen before, this idea of vector functions, where instead we don't have to just be in 2 dimensions, we can be in 3 dimensions or any number of dimensions. And our graphs don't just have to be straight lines, but they can be any shape, and pretty much any shape we could imagine.